From the smallest grains of sand, each one a tiny world unto itself, to the most distant stars, shining like beacons in the vast expanse of space, our universe is composed of atoms, the fundamental units of matter. These tiny particles, too small to be seen by the human eye, are the building blocks of everything we know and experience. From the air we breathe to the ground we walk on, from the water we drink to the stars we gaze upon, atoms are everywhere. But have you ever stopped to wonder where these atoms came from? What is their origin story? How did these tiny particles, brimming with energy and potential, arise from the void? What cosmic events led to their creation? The story of the atom is a story of our universe, a tale that stretches back to the dawn of time. It begins with the Big Bang, an explosion of unimaginable energy that set the universe into motion, creating the first particles. It's a tale of incredible energy, unimaginable forces, and the birth of complexity from an apparent nothingness. Supernovae, the explosive deaths of stars, scattered elements across the cosmos. These elements combine to form complex molecules, the building blocks of planets, stars, and life itself. Join us as we delve into the heart of this cosmic mystery, exploring the origins of the very matter that makes up our world. We will journey through the discoveries of scientists and philosophers who have pondered these questions for centuries, from ancient Greece to modern-day laboratories. Together, we will explore the profound question that has captivated humanity. How did atoms form from nothing? What secrets do they hold about the nature of reality itself? As we unravel the fabric of reality, we may find that the answers lie not just in the stars, but within ourselves, in the very atoms that make us who we are. So let us embark on this journey together, to understand the universe and our place within it, one atom at a time. The quest to understand our universe's origins is one of humanity's oldest and most profound endeavors. For millennia, we've gazed at the stars, pondered the vastness of space, and searched for answers to the fundamental questions of existence. Where did it all begin? How did something come from nothing? The idea that our universe, with its intricate galaxies, brilliant stars, and even life itself, could arise from a state of nothingness is a concept that stretches the limits of our imagination. It seems counterintuitive, paradoxical, even impossible. Yet this is the very mystery that modern physics seeks to unravel. The prevailing scientific theory, known as the Big Bang, posits that our universe began as an incredibly hot, dense point, a singularity, some 13.8 billion years ago. From this point of unimaginable energy, the universe expanded and cooled, setting in motion the chain of events that would ultimately lead to the formation of atoms and everything they compose. But how do we reconcile the idea of a universe bursting forth from nothing with the laws of physics as we understand them? This is where our journey truly begins. A journey that will challenge our understanding of the universe and our place within it. Imagine, if you will, a time before time itself. A time before stars ignited, before galaxies spiraled, before even the very fabric of space and time existed as we know it. This is the realm we must venture into to grasp the formation of atoms from nothing, a realm where our current understanding of physics blurs with the abstract and the unknown. In this primordial abyss, there was no matter, no energy as we perceive it, no familiar laws of physics governing the unfolding of events. Even the concept of nothingness becomes slippery, for in the absence of space and time, how can we even define emptiness? Yet even in this seeming void, the seeds of creation were perhaps already sown. Modern physics, particularly the mind-bending realm of quantum mechanics, suggests that at the smallest scales, reality itself becomes a turbulent sea of uncertainty and potentiality. Imagine a bubbling cauldron where particles and antiparticles constantly flicker in and out of existence, borrowing energy from the void only to disappear in a flash of energy. This ceaseless dance of quantum fluctuations, governed by probabilities and uncertainties, might hold the key to understanding how something can emerge from nothing. While the exact nature of the pre-Big Bang universe remains shrouded in mystery, it's theorized that this quantum realm wasn't static. Imagine instead a universe in constant flux, where quantum fields representing fundamental forces and particles fluctuated wildly, their values shifting and changing like waves on a stormy sea. In this chaotic dance, a tiny region of this quantum sea might have experienced a particularly significant fluctuation, a random blip in the cosmic casino where the fabric of reality itself became momentarily unstable. This instability, this infinitesimal point of extreme density and energy, could have been the seed of our universe. Imagine a tiny bubble, infinitesimally small, suddenly inflating, driven by an unknown repulsive force. This rapid expansion, known as inflation, stretched the fabric of space itself faster than the speed of light, smoothing out any initial wrinkles and irregularities. As this inflationary period ended, the universe continued to expand, but at a less frantic pace. The energy that had been locked within the fabric of space itself was released, transforming into a seething cauldron of particles and antiparticles. This was a universe of extremes, unimaginably hot and dense, governed by forces we're only beginning to comprehend. The fundamental forces of nature, gravity, electromagnetism, the strong and weak nuclear forces, were still intertwined, not yet having differentiated into their distinct identities. Yet even amidst this chaos, a crucial transformation was taking place. The universe, no longer inflating at breakneck speed, began to cool, and as it cooled, the energy of the particles within it began to decrease, setting the stage for the next act in our cosmic drama, the birth of the fundamental building blocks of matter. With the cooling came the decoupling of the fundamental forces, allowing them to exert their individual influences on the nascent universe. This marked a pivotal turning point, for it paved the way for the emergence of the first subatomic particles, the very ingredients from which atoms would eventually be forged. Section 2. A universe ignites. Imagine a moment of unimaginable brilliance, a cosmic dawn where darkness gave way to a blinding flash. This wasn't an explosion in the conventional sense, not something bursting outward into a pre-existing space. This was the very fabric of space and time itself coming into being, expanding at an inconceivable rate. The Big Bang wasn't an event that happened in a specific location, it happened everywhere at once, for everywhere was contained within that infinitesimally small point of origin. It's a concept that defies our everyday intuition, yet it lies at the heart of our understanding of how the universe came to be. In the first infinitesimal fractions of a second after the Big Bang, the universe was a maelstrom of energy, a realm of unimaginable heat and density. Temperatures soared beyond trillions of degrees, far hotter than even the cores of the most massive stars. At these extreme energies, the familiar laws of physics as we know them break down. The four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, were still unified, indistinguishable from one another in this primordial soup. As the universe continued its rapid expansion, it also cooled. And as it cooled, a remarkable transformation began to take place. Imagine a symphony, initially a cacophony of sound, gradually resolving into distinct melodies as instruments find their rhythm and harmony. Similarly, as the universe cooled, the unified force began to separate, like threads in a tapestry slowly unraveling. Gravity, the weakest but most far-reaching force, was the first to become distinct, followed by the strong and weak nuclear forces, and finally, electromagnetism. With the separation of the fundamental forces, the stage was set for the emergence of matter. The immense energy of the early universe couldn't just disappear, it had to transform, guided by Einstein's famous equation E equals mc squared, which tells us that energy and mass are two sides of the same coin. And so, from this sea of energy, particles began to condense, like droplets forming from a cooling vapor. These weren't the atoms we know today, but rather their more fundamental constituents, quarks, leptons, and their antimatter counterparts. The early universe was a chaotic dance of creation and annihilation. Particles and antiparticles, mirror images of each other, constantly collided, their energy transforming back into pure radiation in a flash of light. Yet for reasons that remain one of the greatest mysteries in physics, a subtle imbalance existed. For every billion pairs of particles and antiparticles that annihilated each other, a single particle of matter was left over. This tiny imbalance, this cosmic quirk of fate, was all it took to tip the scales in favor of matter and set the stage for the universe we know. As the universe continued to cool, these leftover particles of matter, quarks and leptons, became the building blocks of everything we see around us. But even then, atoms were still a long way off. The universe was still too hot, too energetic for even these fundamental particles to bind together. Imagine a sea of quarks and gluons, the particles that carry the strong force interacting with incredible intensity. Quarks, the constituents of protons and neutrons, zipped about at near light speed, constantly colliding and exchanging gluons, preventing them from settling into stable configurations. This was a universe still in its infancy, a chaotic soup brimming with potential but yet to find its structure. As the universe expanded and cooled, the searing heat that had kept quarks and gluons in a frenetic dance began to subside. Imagine a cauldron of molten metal, glowing bright orange, gradually cooling and solidifying as the temperature drops. Similarly, the universe, once a seething inferno of energy, was undergoing a crucial transition. As temperatures fell below a critical threshold, the strong force, which had been overwhelmed by the sheer energy of the early universe, began to assert its dominance. The strong force, true to its name, is the most powerful of the fundamental forces. It's the force that binds quarks together to form protons and neutrons, the very heart of atoms. Imagine tiny magnets, irresistibly drawn to each other, snapping together with incredible force. As the universe cooled, the strong force began to gather up quarks, pulling them together into tight-knit groups of three. These groups, bound by the relentless grip of the strong force, were the first protons and neutrons, the building blocks of atomic nuclei. Section 3. The first nuclei. The formation of protons and neutrons was a pivotal step towards the creation of atoms, but the universe was still too hot for even these particles to exist in isolation for long. Imagine a game of high-speed billiards, with protons and neutrons constantly colliding and bouncing off each other with tremendous energy. Occasionally, a proton and a neutron would collide with just the right amount of energy to stick together, forming a simple nucleus, the heart of an atom. But these early nuclei were incredibly fragile, easily blasted apart by the intense heat and radiation that still permeated the universe. The early universe, even as it cooled, was far from a hospitable place. It was a cosmic battlefield filled with a blindingly bright, searingly hot fog of photons, particles of light left over from the Big Bang. Imagine a dense fog, so thick you can barely see your hand in front of your face. But instead of obscuring vision, this fog was a torrent of energy. These photons, constantly colliding with protons and neutrons, prevented the formation of anything more complex than the simplest nuclei. The universe, though teeming with the raw ingredients of atoms, remained a sea of individual particles, unable to combine into anything more substantial. As the universe continued its relentless expansion, it also continued to cool, and as it cooled, a crucial threshold was crossed. The photons, once so energetic, began to lose energy, their wavelength stretching out as the universe expanded. This gradual cooling and stretching of light marked a turning point. Electrons, tiny particles that carry a negative charge, had also emerged from the Big Bang. And as the photons lost energy, they no longer had enough force to prevent electrons from being captured by the positively charged protons in the nuclei. Section 4. Atoms at last. Finally, after almost 380,000 years of cosmic evolution, the conditions were right for the formation of the first true atoms. Imagine a dance, a delicate waltz between electrons and nuclei, drawn together by the electromagnetic force, the invisible hand that governs the interactions between charged particles. Electrons, much lighter than protons and neutrons, began to orbit the nuclei, held in place by the electromagnetic attraction. These simple structures, consisting of a nucleus orbited by electrons, were the first atoms, the building blocks of the world around us. The formation of atoms marked a profound shift in the evolution of the cosmos. Imagine a universe bathed in the warm glow of a setting sun, the light finally able to travel freely through space, no longer scattered by a sea of free electrons. This first light, a faint echo of the Big Bang, can still be detected today, a testament to this pivotal era in cosmic history. With atoms now populating the universe, the stage was set for the emergence of structure on a grand scale. Gravity, once overwhelmed by the intense energy of the early universe, could now exert its pull on these newly formed atoms, drawing them together into vast clouds of gas and dust. While the story of how atoms formed from the primordial soup of the Big Bang is a triumph of modern physics, it's not the end of the story. In fact, it's perhaps more accurate to say that it's just the beginning, for many mysteries remain, hinting at deeper layers of reality yet to be uncovered. The very fact that we can ask these questions, that we can peer so deeply into the universe's past and marvel at its complexity, is a testament to the power of human curiosity and our relentless pursuit of knowledge. One of the most perplexing mysteries in physics is the imbalance between matter and antimatter. For every particle of matter, there exists an antiparticle, identical in mass, but with an opposite charge. When a particle and its antiparticle meet, they annihilate each other in a burst of energy. In the early universe, matter and antimatter should have been created in equal amounts. Yet, we live in a universe dominated by matter. Where did all the antimatter go? Did some subtle asymmetry in the laws of physics tip the scales in favor of matter? Neutrinos, ghostly particles that barely interact with matter, are another piece of the cosmic puzzle. These elusive particles are produced in abundance in stars and nuclear reactions, yet they pass through our bodies and even entire planets as if they weren't even there. Understanding neutrinos is crucial for unraveling the mysteries of the early universe and the processes that drive stars and galaxies. What role did they play in the formation of the first atoms? Can they shed light on the nature of dark matter, the invisible substance that holds galaxies together? Perhaps the most profound mystery of all is the nature of dark matter and dark energy, invisible forces that seem to govern the evolution of the universe on the grandest scales. Dark matter, which makes up about 85% of the matter in the universe, doesn't emit, absorb, or reflect light, making it invisible to our telescopes. Dark energy, on the other hand, is a mysterious force that seems to be accelerating the expansion of the universe. What are these enigmatic entities? Are they fundamentally new forms of matter and energy, or do they point to limitations in our current understanding of physics? The quest to understand how atoms formed from nothing is a journey that takes us to the very edge of human knowledge, where mysteries abound and new discoveries await. It's a journey that requires us to grapple with concepts that stretch the limits of our imagination, from the infinitesimal scales of quantum mechanics to the vast expanse of the cosmos. Yet it's a journey well worth taking, for it's in unraveling the mysteries of the universe that we gain a deeper appreciation for its beauty, its complexity, and our place within it. The story of the atom is ultimately a story about ourselves, a story about the fundamental building blocks of everything we know and love, forged in the fiery crucible of the Big Bang. Our journey into the heart of matter has taken us from the unimaginable void before time, a vast expanse of nothingness where not even the concept of time existed. This void, this emptiness, was the canvas upon which the universe would eventually be painted. From this primordial void emerged the first atoms, the fundamental building blocks of our universe. These atoms, simple yet profound, were the seeds from which all matter would grow. They were the first whispers of existence in a silent cosmos. We've delved into the realm of quantum fluctuations, a mysterious domain where particles flicker in and out of existence, borrowing energy from the vacuum itself. In this quantum dance, particles appear and vanish, a testament to the strange and wondrous nature of the subatomic world. We've witnessed the awesome power of the Big Bang, the cataclysmic event that marked the birth of space and time. This explosion was not just a release of energy, but the very moment when the universe began to expand, setting the stage for everything that would follow. In the crucible of the early universe, the lightest elements were forged. Hydrogen and helium, the simplest of atoms, were created in a process known as nucleosynthesis. These elements would become the building blocks for stars, galaxies, and eventually, life itself. The story of how atoms formed from nothing is a testament to the power of scientific inquiry. Through relentless curiosity and rigorous research, scientists have pieced together the history of the universe, revealing the processes that transformed nothingness into the rich tapestry of existence we see today. Our ability to piece together the universe's history from the faintest whispers of light is nothing short of miraculous. The light from distant stars and the cosmic microwave background radiation serve as time capsules, carrying information from the dawn of time to our present day. By studying the smallest constituents of matter, we gain insights into the fundamental nature of the universe. Subatomic particles, with their intricate structures and interactions, hold the keys to understanding the very fabric of reality. It's a story that challenges our intuition, pushing us to expand our minds to encompass concepts that defy everyday experience. The journey from nothingness to existence is not just a scientific endeavor, but a philosophical one, prompting us to ponder our place in the cosmos. As we continue to explore the expanding universe, we are constantly confronted with mind-bending scientific theories that stretch the limits of our understanding. Each discovery brings us closer to unraveling the mysteries of existence, yet also reveals how much more there is to learn. From the formation of galaxies to the birth of stars, the universe is a dynamic and ever-evolving entity. Each moment in its history is a chapter in the grand story of existence, a story that we are only beginning to understand. And as we look up at the stars, we are filled with a sense of wonder and curiosity. The journey from nothingness to existence is not just the story of the universe, but the story of us all. It is a journey that continues to inspire and captivate, urging us to keep exploring, keep questioning, and keep dreaming. As we've explored the formation of atoms, we've uncovered a profound truth. We are all connected to the cosmos in a fundamental way. The very atoms that make up our bodies, the air we breathe, the earth beneath our feet, they all were forged in the heart of stars or during the first fleeting moments after the Big Bang. Each atom carries within it a legacy of cosmic evolution, a story spanning billions of years. When we look up at the stars, we're not just gazing at distant objects. We're looking at the echoes of the processes that created us, the echoes of the universe coming into being. While we've learned a great deal about the formation of atoms, our understanding of the universe is still in its infancy. The intricate dance of particles, the forces that bind them, and the very fabric of space-time itself are subjects of endless fascination and study. Our journey is far from over. Each discovery opens up new questions, new avenues of exploration that beckon us to delve deeper into the mysteries of the cosmos. The universe, it seems, is full of surprises, each more wondrous than the last. From the smallest subatomic particles to the vast expanses of intergalactic space, there is always something new to learn, something new to discover. Mysteries that beckon us to venture further into the unknown. The quest for knowledge is a journey without end, a path that leads us ever onward, ever deeper into the heart of the cosmos. The nature of dark matter and dark energy, two of the most enigmatic substances in the universe, continues to elude us. These invisible forces shape the structure of the cosmos, yet their true nature remains a profound mystery. The imbalance between matter and antimatter, a puzzle that has intrigued scientists for decades, holds the key to understanding the very origins of the universe. Why does matter dominate over antimatter? What processes led to this asymmetry? The elusive properties of neutrinos, ghostly particles that pass through matter almost undetected, offer tantalizing clues to the fundamental workings of the universe. These tiny particles, so difficult to study, may hold the answers to some of the most profound questions in physics. These are just a few of the cosmic puzzles that continue to captivate scientists. Each discovery, each new piece of data, brings us one step closer to understanding the true nature of the universe. But perhaps the greatest mystery of all is the very fact that something exists rather than nothing. The existence of the universe, with all its complexity and beauty, is a question that has puzzled philosophers and scientists alike for centuries. How can we comprehend a universe springing forth from a state of utter nothingness? The Big Bang Theory, our best explanation for the origin of the universe, raises as many questions as it answers. What sparked the Big Bang? What conditions led to the birth of the universe? These are questions that challenge the very limits of our understanding, pushing us to explore new theories and new ideas. These are questions that may forever lie beyond the reach of science, yet they inspire us to push the boundaries of our knowledge, to seek answers in the face of the unknown. pushing us to confront the limits of our understanding. The pursuit of knowledge is a journey of discovery, a quest that drives us to explore the deepest mysteries of the universe. Yet even if we never find definitive answers, the very act of asking these questions, of seeking to understand the universe, is a testament to the human spirit. The very act of asking these questions, of searching for meaning and understanding in the vast cosmic scheme of things, is a testament to the human spirit, our insatiable curiosity, and our enduring connection to the universe we inhabit. Our insatiable curiosity drives us to explore, to seek out new knowledge, to push the boundaries of what we know and understand. It is this curiosity that has led to some of the greatest discoveries in the history of science. It is a testament to the human spirit, our insatiable curiosity, and our enduring connection to the universe we inhabit. The exploration continues, driven by the same sense of wonder that has captivated humanity since we first gazed up at the starry sky and pondered our place in the cosmos. The exploration continues, driven by the same sense of wonder that has captivated humanity since we first gazed up at the starry sky and pondered our place in the cosmos. Each new discovery, each new piece of knowledge, brings us one step closer to understanding the true nature of the universe. Driven by the same sense of wonder that has captivated humanity since we first gazed up at the starry sky and pondered our place in the cosmos. The journey of exploration is unending, a testament to the enduring human spirit and our insatiable curiosity. Section 5. The first nuclei. From the moment we first gaze upon a star-dusted sky, we are filled with questions. Where did it all come from? What are those twinkling points of light? And how did we, with our complex bodies and curious minds, arise from this vast and ancient cosmos? In this exploration, we journey into the heart of these questions, diving deep into the crucible of creation to understand the birth of elements. Our story begins not with planets or stars, but with the fundamental building blocks of matter themselves. These are the elements, the ingredients listed on the periodic table, each with its unique story to tell. From the simplest atom, hydrogen, to the heavier elements that make up our planet and even our own bodies, every atom carries within it the echo of the universe's tumultuous beginnings. Understanding the origin of elements is to understand our own cosmic ancestry. It's about tracing the lineage of the very atoms that make up our bodies back to the fiery furnace of the Big Bang and the hearts of long-dead stars. The universe, in its infancy, was a vastly different place than the cosmos we observe today. It was a hot, dense soup of energy and particles, expanding rapidly in the aftermath of the Big Bang. Yet, within this chaotic environment, the seeds of order were already being sown. As the universe cooled, energy began to condense into matter, following the elegant dictates of Einstein's famous equation, E=mc². The first element to emerge from this cosmic alchemy was hydrogen, the simplest and most abundant element in the universe. Alongside it, a small amount of helium, the second lightest element, also formed. These two elements, hydrogen and helium, formed the primordial soup from which the first stars would eventually ignite. They represent the direct products of the Big Bang, the fundamental building blocks upon which the universe's grand symphony of creation would be played. But the story doesn't end there. The universe, as we know, is filled with a rich diversity of elements, far beyond the simple hydrogen and helium formed in the Big Bang's afterglow. So how did this incredible diversity arise? The answer lies in the hearts of stars, the cosmic furnaces where elements are forged through the awe-inspiring process of nuclear fusion. Within the intense heat and pressure of a star's core, hydrogen atoms are forced to fuse together, creating helium and releasing a tremendous amount of energy in the process. This energy, in the form of light and heat, is what causes stars to shine. But the fusion process doesn't stop at helium. As stars age, they begin to fuse helium into heavier elements, such as carbon, oxygen, and nitrogen. This process continues, creating increasingly heavier elements, each layer within the star representing a different stage in this cosmic alchemy. The heavier the element, the higher the temperature and pressure required to create it. Imagine the early universe not as an empty expanse, but as a cosmic kitchen bustling with activity. The Big Bang's intense heat cooled, allowing protons, neutrons, and electrons to condense. These particles were the raw materials for the universe's grand culinary experiment. In this chaotic kitchen, temperatures were still astronomically high. Amidst this, the strong nuclear force acted as the master chef. It pulled protons and neutrons together, forming deuterium. This was a pivotal moment in the universe's history, leading to the creation of every element we know. For roughly the first 380,000 years after the Big Bang, the universe remained a turbulent sea of protons, neutrons, electrons, and a smattering of deuterium nuclei. This era, known as the Hydrogen Epoch, was a time of darkness, devoid of the brilliant stars and galaxies that grace our night sky today. Light, you see, couldn't travel freely through this chaotic soup. The universe was still too hot and dense. Photons, constantly colliding with charged particles, were trapped, unable to traverse any significant distance. Imagine a dense fog obscuring everything beyond a few feet. That was the early universe during the Hydrogen Epoch. But as the universe continued to expand and cool, a crucial transition was on the horizon. The temperature dropped to a point where electrons, once zipping around freely, could finally be captured by the positively charged protons. This marked the formation of the first atoms, the building blocks of the matter we see around us. And with the formation of these first atoms, a profound change swept through the universe. Light, no longer held captive by a sea of charged particles, was finally free to travel unimpeded. The universe, once a murky fog, became transparent. The formation of the first atoms ushered in a new era in the universe's evolution. Gravity, now able to exert its influence over larger distances, began to draw together vast clouds of hydrogen and helium gas. These clouds, colossal in scale, were the birthplaces of the first stars. Within these collapsing gas clouds, pressure and temperature soared as gravity relentlessly pulled matter inward. At the cores of these collapsing giants, temperatures reached a staggering 10 million degrees Celsius, hot enough to reignite the nuclear fires that had briefly flickered during the universe's first few minutes. Under these extreme conditions, hydrogen nuclei, crammed together with unimaginable force, overcame their natural electrostatic repulsion. The strong nuclear force once again took center stage, fusing hydrogen nuclei together, forming helium and releasing a tremendous amount of energy in the process. This energy, radiating outward from the star's core, pushed back against the inward pull of gravity, creating a delicate balance, the defining characteristic of a star. The first stars had ignited, flooding the universe with their brilliant light, their nuclear furnaces forging the first helium nuclei since the Big Bang. The first stars were cosmic pioneers, their nuclear fires blazing with a ferocity unmatched by their modern counterparts. But their hydrogen fuel, though plentiful, was not infinite. As these stellar giants aged, the helium ash from their hydrogen fusion began to accumulate in their cores. Helium, heavier than hydrogen, required even greater temperatures and pressures to fuse. For stars similar in mass to our Sun, the fusion of helium into heavier elements marks the beginning of their end. They eventually shed their outer layers, leaving behind a dense, white dwarf star. But for stars significantly more massive than our Sun, the journey into the heart of matter had only just begun. The relentless crush of gravity within these stellar behemoths pushed temperatures and pressures to even more extreme levels, igniting helium fusion in their cores. Two helium nuclei, colliding with unimaginable force, fused to create beryllium. This unstable element, in turn, could capture another helium nucleus, forming a stable carbon nucleus. The universe had taken its next momentous step up the periodic ladder, forging the element that forms the backbone of all life on Earth. The first stars, however, were not destined to last forever. Their fiery lives, though lasting millions or even billions of years, would eventually come to an end. And in their death throes, these stellar pioneers would seed the cosmos with the elements they had forged in their nuclear hearts. As massive stars exhaust their nuclear fuel, they reach a critical tipping point. The outward pressure from nuclear fusion can no longer counter the relentless inward pull of gravity. The star's core collapses in on itself, triggering a catastrophic explosion, a supernova. Supernovae are among the most violent and energetic events in the universe. For a brief moment, a single star can outshine an entire galaxy, and within the cauldron of a supernova explosion, temperatures and pressures reach unimaginable extremes, forging elements far heavier than iron, including gold, platinum, and uranium. The shockwaves from these stellar explosions ripple through space, compressing nearby clouds of gas and dust. These enriched clouds, seeded with the elements forged in the hearts of long-dead stars, become the nurseries for new generations of stars and planetary systems. Deep within the heart of a massive star, far hotter and denser than our sun, a cosmic ballet unfolds. Hydrogen, exhausted by eons of fusion, has given way to a core of helium. This helium, now the star's primary fuel, faces a greater challenge, a higher energy barrier that must be overcome to continue the stellar furnace's relentless burn. Temperatures soar to hundreds of millions of degrees Celsius, pressure unimaginable in the human experience. Helium nuclei, forced together by this cosmic vice, collide with incredible force. Most bounce off, repelled by their mutual positive charge. But occasionally, a collision occurs with enough energy to overcome the electromagnetic barrier, allowing the strong nuclear force to bind them together. The result, a nucleus of beryllium, a fleeting element unstable in our familiar world. Yet in this stellar crucible, beryllium exists long enough to capture another helium nucleus, transforming into carbon. This carbon, a cornerstone of life as we know it, is the first significant step beyond the Big Bang's primordial elements. The star, once a simple sphere of hydrogen, now harbors a growing core of carbon, a testament to the immense forces at play within its heart. This carbon core, however, is but the beginning, a stepping stone on the path to even heavier elements, each with its own role to play in the grand cosmic narrative. Section 6. Carbon, the foundation of life. Carbon, born from the fusion of 3 helium nuclei, is a unique and remarkable element. Unlike its lighter siblings, hydrogen and helium, carbon possesses a remarkable ability to bond with itself and other elements, forming long chains and complex structures. This ability, known as catenation, is the foundation of organic chemistry, the chemistry of life itself. Carbon atoms, linked together in intricate chains and rings, form the backbone of proteins, carbohydrates, lipids, and nucleic acids, the essential molecules that make up all living organisms on Earth. Without carbon, our planet would be a barren and lifeless rock. The carbon forged in the hearts of long-dead stars forms the very fabric of our bodies, the air we breathe, the food we eat. It is a testament to the profound interconnectedness of the cosmos, a reminder that we are, in a very real sense, children of the stars. But carbon's story doesn't end with the building blocks of life. It plays a crucial role in the evolution of stars themselves, influencing their lifespans, their colors, and their ultimate fates. Carbon, in many ways, is the unsung hero of the cosmic drama. As the carbon core of a massive star continues to grow, temperatures and pressures climb ever higher, reaching a point where carbon itself can fuse. This next stage in stellar nucleosynthesis is a crucial one, for it gives rise to oxygen, the element that makes up over 20% of our atmosphere and is essential for most life on Earth. Carbon nuclei, forced together under unimaginable pressure, overcome their mutual repulsion and merge, forming a variety of heavier nuclei. One of the most common outcomes is the creation of oxygen, born from the fusion of 2 carbon nuclei. Oxygen, like carbon, is a versatile element, readily forming bonds with other elements to create a vast array of compounds. It is a key component of water, the universal solvent that is essential for life as we know it. Oxygen is also a vital ingredient in the rocky planets like our Earth, forming the silicates that make up their crusts and mantles. The abundance of oxygen in the universe is a direct consequence of the life cycle of stars, particularly massive stars that end their lives in spectacular supernova explosions. These cosmic events, while marking the death of a star, also serve as the birth cries of new elements, scattering the building blocks of planets and life itself across the cosmos. The stellar furnace, once ignited, continues its relentless work, forging a succession of heavier elements, each with its own unique properties and cosmic significance. Nitrogen, a key component of our atmosphere and a vital nutrient for life, is formed through a complex series of reactions involving carbon and oxygen. Neon, a noble gas known for its vibrant glow in neon signs, is also born in the hearts of stars. Although less abundant than carbon or oxygen, neon plays an important role in the evolution of stars, influencing their internal structure and energy transport. Fluorine, a highly reactive element used in a variety of industrial applications, is another product of stellar nucleosynthesis. Though less familiar than its cosmic siblings, fluorine is a testament to the incredible diversity of elements that can be created within the extreme environments of stars. The creation of these heavier elements is not a linear process. It involves a complex network of nuclear reactions with multiple pathways leading to the same element. The precise abundances of elements forged within a star depend on its mass, its composition, and the specific conditions within its core. As a massive star's core collapses, temperatures and pressures soar. Elements lighter than iron fuse, releasing energy and delaying gravity's crush. Iron, element 26, marks a critical turning point. Its fusion requires more energy than it releases, leading to the star's demise. This sets the stage for a supernova explosion, forging elements heavier than iron. Iron is both a testament to stellar nucleosynthesis and a harbinger of explosive death. When a massive star's iron core collapses, gravity takes over. The core collapses, triggering a shockwave that blasts the star's outer layers. This supernova briefly outshines an entire galaxy. Elements heavier than iron are forged through neutron capture. Supernovae scatter these elements, seeding the cosmos with the building blocks of planets and life. The birth and death of stars are integral to a grand cosmic cycle. Massive stars forge heavy elements and scatter them in their explosive deaths. These ashes coalesce into new stars and planetary systems. Our solar system formed from remnants of countless supernovae. Each generation of stars enriches the universe, connecting us to the cosmos. The story of element formation is about us. Every atom in our bodies was forged in a star. We are stardust, products of stellar birth, life, and death. Understanding element origins reveals our place in the cosmos. We are connected to the universe, witnessing the legacy of stellar alchemy. The universe is a dynamic tapestry of creation and destruction. Supernovae, the explosive deaths of massive stars, are cosmic engines of creation. They forge heavy elements and scatter them, seeding the cosmos. A star's core collapses, triggering a shockwave that rips through its outer layers. This shockwave sets off nuclear fusion, briefly outshining a galaxy. Supernovae are both endings and beginnings in the cosmic drama. Supernovae are classified into different types. Type 2 supernovae occur when a massive star's core collapses. Protons and electrons form neutrons, releasing neutrinos. The shockwave heats and compresses the star's outer layers, forging new elements. These elements are blasted into space, enriching the interstellar medium. The aftermath of a supernova is both destruction and creation. Depending on the star's mass, a neutron star or black hole may remain. Neutron stars are incredibly dense, while black holes have gravity so strong that nothing can escape. These remnants play crucial roles in galaxy evolution. Neutron stars power phenomena like pulsars, while black holes influence star and gas cloud motions. Stellar remnants born from death shape the universe. Supernovae announce their presence with cosmic rays. These particles, accelerated by shock waves, bombard our planet. Cosmic rays provide clues about their origins and extreme environments. Studying them reveals the violent processes shaping our galaxy. The interstellar medium, ISM, is a mixture of gas and dust. Supernovae enrich the ISM with heavier elements. Shockwaves from supernovae trigger molecule formation and seed the ISM. This enrichment influences the formation of new stars and planetary systems. Section 7. From Supernovae to Solar Systems, A New Beginning. A star's death marks a new beginning in the cosmic cycle. Ejected material cools and forms molecular clouds, birthing new stars. Gravity draws gas and dust into clumps, igniting nuclear fusion. The protoplanetary disk around a newborn star forms planets, enriched by heavy elements. Stellar birth, life, and death enrich galaxies with heavier elements. This creates a cosmic tapestry of varying chemical abundances. Studying these compositions reveals the history of star formation and galaxy evolution. The deaths of stars provide seeds for new generations, increasing the universe's complexity. The study of element formation explores the universe's diversity. From hydrogen fusion to supernovae, it's a testament to nuclear physics. Many questions remain about supernovae and other phenomena. This quest drives astronomers to unlock the secrets of element formation and our place in the cosmos. Our understanding of the cosmos has been built upon the foundations laid by generations of curious minds. The story of element formation is no different. It's a narrative interwoven with the brilliance and perseverance of pioneers. Long before powerful telescopes, our ancestors sought answers in the night sky. Ancient astronomers laid the groundwork for modern astronomy. Fast forward to the 19th century, a period of remarkable scientific advancements. Joseph von Fraunhofer made a groundbreaking discovery. He observed dark lines in the spectrum of sunlight, now known as Fraunhofer lines. These lines represented the fingerprints of elements in the sun's atmosphere. Fraunhofer's discovery allowed astronomers to probe the chemical composition of celestial objects. It linked the elements found on Earth to the distant stars and nebulae. The early 20th century witnessed a revolution in physics, with groundbreaking discoveries in quantum mechanics and relativity reshaping our understanding of the universe on a fundamental level. This revolution extended to astrophysics, where scientists began to apply these new insights to unravel the mysteries of stars and galaxies. At the forefront of this astrophysical revolution was Cecilia Payne-Gaposchkin, a brilliant young astronomer who made one of the most profound discoveries of the 20th century. The realization that stars, those distant suns scattered across the cosmos, are composed primarily of hydrogen and helium. Payne-Gaposchkin's discovery, published in her 1925 doctoral thesis, was nothing short of revolutionary. At the time, it was widely believed that stars had a similar chemical composition to Earth, with heavier elements like iron and silicon being the most abundant. But Payne-Gaposchkin's meticulous analysis of stellar spectra, using the principles of quantum mechanics to interpret the observed spectral lines, revealed otherwise. Her work, initially met with skepticism, ultimately reshaped our understanding of stellar evolution and the processes that govern the birth, life, and death of stars. It laid the groundwork for the development of stellar models that could accurately predict the temperatures, luminosities, and lifespans of stars based on their mass and chemical composition. While Payne-Gaposchkin was revolutionizing our understanding of stellar composition, another groundbreaking discovery was taking place that would forever change our view of the cosmos. Edwin Hubble's observation that the universe is expanding. Hubble, an American astronomer, used the powerful Hooker telescope at Mount Wilson Observatory to measure the distances and velocities of distant galaxies. To his astonishment, he found that almost all galaxies were moving away from us, and the farther away a galaxy was, the faster it was receding. This relationship, now known as Hubble's law, had profound implications for our understanding of the universe. If the universe is expanding, it means that it must have been smaller and denser in the past, leading to the idea of the Big Bang, the event that marked the birth of space and time. The discovery of the expanding universe provided a crucial piece of the puzzle for understanding element formation. The extreme temperatures and densities of the early universe, predicted by the Big Bang model, created the perfect conditions for the first elements, hydrogen and helium, to be forged in the crucible of creation. The story of element formation is not just a tale of astronomical observations, but also a testament to the remarkable progress made in nuclear physics throughout the 20th century. The discovery of the atomic nucleus, the realization that atoms are not indivisible but composed of smaller particles, and the development of quantum mechanics all played crucial roles in understanding the processes that govern the behavior of matter at the subatomic level. Scientists like Ernest Rutherford, Marie Curie, and Enrico Fermi pioneered the study of radioactivity, nuclear fission, and nuclear fusion, laying the groundwork for our understanding of how elements are created and transformed in the hearts of stars and in the extreme environments of supernovae explosions. The development of particle accelerators, such as the cyclotron and the synchrotron, allowed physicists to create and study subatomic particles in controlled laboratory settings, providing crucial insights into the fundamental forces that govern the interactions of these particles and the processes that drive stellar nucleosynthesis. The marriage of nuclear physics and astrophysics has been a fruitful one, with each discipline informing and inspiring the other, leading to a deeper understanding of the universe and our place within it. The quest to understand the origin of the elements is far from over. While we have made remarkable progress in deciphering the cosmic code, many mysteries remain, driving astronomers and physicists to develop ever more sophisticated tools and techniques to probe the universe's intricate workings. New generations of telescopes, both ground-based and space-based, are being designed and built, equipped with advanced instruments capable of peering farther into space, observing fainter objects, and analyzing light in greater detail than ever before. Astronomers are also increasingly turning to computer simulations to model the complex processes that govern the evolution of stars, galaxies, and the universe as a whole. These simulations, run on powerful supercomputers, allow scientists to explore a wide range of scenarios and test theoretical models against observational data. The study of element formation is a journey of discovery that shows no signs of slowing down. As we continue to explore the cosmos with increasingly powerful tools and innovative techniques, we can look forward to unraveling more secrets of the universe and gaining a deeper appreciation for the remarkable processes that have shaped the world around us and the very atoms from which we are made. Our journey reveals a cosmos far more interconnected and wondrous than we could have imagined. From hydrogen and helium to the rich diversity of elements, the universe's creativity is unceasing. Gravity draws gas and dust together, igniting nuclear furnaces within stars. Stellar crucibles fuse lighter elements into heavier ones, transforming the universe. Each element carries a unique history, a tale of cosmic origin. It's a story that spans unimaginable scales of space and time. The atoms in our bodies were once part of distant stars, forged in supernovae billions of years ago. We are children of the stars, our existence intertwined with the cosmic cycle. This truth humbles and empowers us, reminding us of our extraordinary nature. As we look up at the night sky, let us remember our shared cosmic heritage. Section 8. Building the universe, how atoms combine to form galaxies and stars. From the moment we first gaze upon a starlit sky, we are filled with a sense of wonder and awe. The vastness of space, dotted with countless celestial objects, sparks within us a primal curiosity about our place in the cosmos. How did this grand symphony of stars, galaxies, and cosmic phenomena come to be? How did the universe, in all its complexity and beauty, arise from the simplest of ingredients? These are questions that have captivated humanity for millennia, driving us to explore the furthest reaches of space and time. In this exploration of the cosmos, we embark on a journey to uncover the secrets of the universe's construction. We delve into the heart of stars where atomic furnaces forge the elements that make up everything we know, from the air we breathe to the ground beneath our feet. We witness the intricate dance of gravity, pulling together vast clouds of gas and dust to ignite the fiery birth of stars. And we marvel at the intricate tapestry of galaxies, woven together by the threads of dark matter and cosmic expansion. Join us now as we journey through the cosmos, unraveling the mysteries of the universe's construction and gaining a deeper appreciation for the intricate processes that have shaped the cosmos as we know it. Our journey begins with the smallest of particles, the building blocks of matter itself, and leads us to the grandest structures in the universe, revealing the interconnectedness of all things cosmic. Our universe is a vast and complex place, a cosmic ocean teeming with celestial wonders. Yet, for all its apparent complexity, the universe is built from surprisingly simple ingredients. Atoms, the fundamental building blocks of matter, hold the key to understanding how the universe in all its grandeur came to be. Like tiny Lego bricks, atoms combine and recombine in countless ways to form the molecules, structures, and celestial objects that populate the cosmos. Imagine, if you will, the vast clouds of gas and dust that permeate interstellar space. These clouds, remnants of ancient stars and the raw materials for future generations, are the nurseries of stars and planetary systems. Within these cosmic clouds, atoms, forged in the fiery hearts of long-dead stars, begin their journey to create something new. Hydrogen, the simplest and most abundant element in the universe, plays a crucial role in this cosmic construction project. Under the influence of gravity, hydrogen atoms are drawn together, their tiny masses exerting an irresistible pull on one another. As these atoms draw closer, they collide with increasing speed and frequency, generating heat and pressure within the collapsing cloud. This process of gravitational collapse is the driving force behind the formation of stars, galaxies, and the very structure of the universe itself. As we delve deeper into this cosmic dance, we will uncover the intricate mechanisms by which atoms, drawn together by gravity's invisible hand, give rise to the awe-inspiring celestial tapestry that surrounds us. We begin our exploration at the smallest of scales, in the realm of atoms, where the fundamental forces of nature orchestrate a delicate dance of attraction and repulsion. Atoms, far from being solid, indivisible particles, are miniature universes composed of protons, neutrons, and electrons. Protons, positively charged, reside within the atom's nucleus, while electrons, negatively charged, whirl around the nucleus in a blur of quantum energy. This balance of charges holds atoms together. Atoms interact, forming bonds that create molecules, the building blocks of our world. Imagine two hydrogen atoms approaching in space. Their electrons repel each other, creating a force that pushes the atoms apart. Yet gravity, the invisible hand shaping the cosmos, exerts its influence. Though weak, gravity draws atoms closer, overcoming electrostatic repulsion. This interplay of forces lies at the heart of chemical bonding and molecule formation. From these interactions, the building blocks of stars, planets, and life are formed. As atoms draw closer, overcoming the initial electrostatic repulsion, their electrons begin to interact in fascinating ways. No longer confined to orbiting a single nucleus, the electrons enter into a shared dance, forming a kind of cosmic ballet around the two nuclei. This shared dance of electrons is the essence of a chemical bond, a force that holds atoms together to form molecules. In the case of our hydrogen atoms, this dance results in the formation of a molecule of hydrogen gas, denoted as H2. This simple molecule, consisting of just two hydrogen atoms locked in a gravitational embrace, is the most abundant molecule in the universe, forming the vast clouds of gas that pervade interstellar space. But the cosmic dance doesn't stop there. Within the swirling chaos of a gas cloud, countless atoms collide and interact, forming a dizzying array of molecules. Oxygen atoms, with their 6 outer electrons, readily form bonds with other elements, creating molecules like water, H2O, carbon dioxide, CO2, and countless others. Carbon, with its unique ability to form 4 bonds, acts as a kind of molecular Lego brick, able to link with itself and a wide variety of other elements to create complex chains, rings, and branching structures. These carbon-based molecules, known as organic molecules, form the very basis of life as we know it. From the simplest molecules like hydrogen gas to the complex organic molecules that make up our DNA, the formation of molecules from atoms represents a crucial step in the universe's journey from simplicity to complexity. These molecules, borne aloft on currents of gas and dust, become the raw materials for the next stage in the universe's grand construction project, the formation of stars. Immense clouds of gas and dust drift through interstellar space. These clouds, remnants of ancient supernova explosions, are cosmic nurseries where gravity sculpts the universe. Gravity pulls the cloud inward, attempting to collapse it. Atoms and molecules within the cloud create an outward pressure that resists gravity's pull. Over time, gravity gains the upper hand. Denser regions grow, drawing in more gas and dust. This marks the beginning of a star's life, transforming gas and dust into a brilliant beacon of light. As the denser regions within the cloud collapse under their own gravity, they begin to heat up. The gravitational potential energy of the infalling gas and dust is converted into kinetic energy, causing the particles to collide with increasing speed and frequency. This frenetic dance of particles generates heat, raising the temperature at the cloud's core to millions of degrees. At the heart of this swirling inferno, a protostar emerges, a dense hot ball of gas that is not yet a true star, but is well on its way. The protostar's immense gravity continues to draw in material from the surrounding cloud, increasing its mass and temperature. However, The protostar's journey to stardom is not without its challenges. As the core heats up, the pressure within the protostar increases dramatically. This outward pressure, generated by the intense heat and the increasing density of the core, pushes back against gravity's relentless inward pull. A tug-of-war ensues, a delicate balancing act between gravity's desire to crush the protostar and the outward pressure generated by the inferno at its core. This struggle between gravity and pressure determines the protostar's fate, shaping its evolution and ultimately determining whether it will ignite into a brilliant star or collapse under its own weight. As the protostar continues to accrete material from the surrounding cloud, its core temperature and pressure continue to rise. The fate of the protostar hangs in the balance, a cosmic drama played out on a grand scale, with the forces of gravity and pressure locked in a titanic struggle for dominance. Deep within the collapsing cloud, the protostar's core continues to heat up, reaching temperatures unimaginable on Earth. Millions of degrees Celsius, then tens of millions, the pressure building to an almost inconceivable level. Atoms, once content to dance around each other, are now forced into a frenetic mosh pit, their nuclei smashing together with unimaginable force. This is the crucible of creation, the heart of a nascent star, and at a critical temperature around 10 million degrees Celsius, something truly remarkable occurs, a process that will define the very essence of the star's existence: nuclear fusion. Hydrogen atoms, the simplest and most abundant element in the universe, are the fuel for this stellar fire. Under the immense pressure and temperature at the protostar's core, hydrogen nuclei, each a single proton, are forced to overcome their natural electrostatic repulsion and fuse together. This fusion process, a ballet of subatomic particles, releases an almost unimaginable amount of energy. This energy, radiating outward from the core, pushes back against the relentless crush of gravity. A new equilibrium is reached, a delicate balance between the inward pull of gravity and the outward push of fusion energy. This is the moment a protostar truly becomes a star, a self-sustaining nuclear furnace, radiating light and heat across vast distances of space. With the onset of nuclear fusion, a star enters a state of stellar equilibrium, a delicate balancing act between the inward pull of gravity and the outward pressure generated by the nuclear reactions at its core. This equilibrium is not static, but rather a dynamic interplay of forces that will persist for millions, even billions of years, shaping the star's life and ultimate fate. Imagine a star as a giant cosmic balloon. Gravity, like the air surrounding the balloon, constantly tries to compress it, to make it smaller. But the nuclear reactions within the star's core, like the air pumped inside the balloon, push outward, resisting gravity's relentless squeeze. This balance, however, is not always perfect. Slight fluctuations in the rate of nuclear fusion or changes in the star's internal structure can cause the star to expand or contract, seeking to restore equilibrium. These subtle shifts in size and luminosity, often occurring over vast timescales, are a testament to the dynamic nature of stars, constantly adjusting and adapting to maintain their internal balance. The life of a star is a constant struggle against gravitational collapse, a battle fought and won every moment within its fiery heart. As long as a star has a supply of hydrogen fuel to power its nuclear furnace, it can maintain this delicate balance, shining brightly and illuminating the cosmos. The life of a star, from its fiery birth in a collapsing cloud of gas and dust to its eventual demise, is a story of cosmic evolution. The path a star takes, its lifespan and its fate, are all determined by its mass. Stars like our Sun live long and relatively peaceful lives. They spend billions of years fusing hydrogen into helium, radiating energy into space. More massive stars live fast and die young. Their immense gravity drives nuclear fusion at a furious rate. These giants blaze with incredible luminosity, burning through their hydrogen fuel quickly. As stars age, they exhaust their hydrogen fuel, and their cores contract. This heats the core, igniting the fusion of helium into heavier elements. The star expands, becoming a red giant, engulfing nearby planets. The final stages of a star's life are a dramatic display of cosmic fireworks. Smaller stars form planetary nebulae, their cores contracting into white dwarfs. Massive stars end in a supernova explosion, one of the most energetic events in the universe. The cosmos is a tapestry woven with stars of all sizes, luminosities, and colors. From the dimmest red dwarfs to the brilliant blue supergiants, the universe showcases stellar diversity. Between these extremes lie a variety of stellar types, each with its own unique characteristics and evolutionary path. Section 9. The role of supernovae, cosmic alchemy, and the seeds of life. Supernovae, the explosive deaths of massive stars, play a crucial role in the cycle of stellar birth and death. These cosmic cataclysms enrich the interstellar medium with heavy elements, triggering the formation of new stars and planets. The very atoms that make up our bodies were once forged in the heart of a dying star, scattered across the cosmos in a supernova explosion. Galaxies, vast collections of stars, gas, dust, and dark matter, are organized into intricate cosmic webs, clusters, and superclusters, shaped by gravity. Gravity continued to shape the distribution of galaxies, drawing them together into clusters and superclusters, vast cosmic structures connected by filaments of gas and dark matter. Spiral galaxies, like our own Milky Way, are among the most beautiful objects in the cosmos. Their graceful spiral arms, traced out by young, hot blue stars, are a testament to the intricate interplay of gravity, rotation, and star formation. As density waves sweep through the interstellar medium, they compress gas and dust, triggering bursts of star formation. Section 10. The Milky Way, our galactic home. Nestled within the vastness of the cosmos lies our own galaxy, the Milky Way, a barred spiral galaxy spanning some 100,000 light-years across. The Milky Way's spiral arms, traced out by young, hot blue stars and illuminated by glowing nebulae, are regions of intense star formation. Our own solar system resides in one such spiral arm, the Orion Arm, located about 26,000 light-years from the galactic center. Over billions of years, galaxies interact with one another, their gravitational fields distorting their shapes, triggering bursts of star formation, and even leading to spectacular collisions and mergers. Despite the violence of these encounters, galactic collisions can be incredibly creative, triggering the formation of new generations of stars and reshaping galaxies. The Milky Way itself is thought to have undergone several mergers throughout its history, accreting smaller galaxies and reshaping its structure over billions of years. The universe, far from being a static and unchanging realm, is in a constant state of expansion. This expansion, a fundamental property of the universe itself, was first discovered in the 1920s by astronomer Edwin Hubble. The expansion of the universe is one of the most fundamental discoveries in modern astronomy, providing us with a glimpse into the history of the cosmos and shaping our understanding of its ultimate fate. While we can observe and study the luminous matter in the universe, stars, galaxies, gas, and dust, there is another, more elusive component that plays a crucial role in shaping the cosmos: dark matter. This invisible substance, so called because it does not interact with light, makes up the vast majority of the matter in the universe, yet its true nature remains one of the greatest mysteries in modern astrophysics. The existence of dark matter is inferred from its gravitational effects on visible matter. We've journeyed from the birth of atoms in the crucible of the Big Bang to the majestic sweep of spiral galaxies. But our exploration of the cosmos would be incomplete without confronting its most baffling mysteries. And perhaps no cosmic puzzle is as perplexing as the enigma of dark matter. We know dark matter exists because of its gravitational effects on the visible universe. The search for dark matter is a profound quest, a journey into the heart of the universe's unseen realm. As if the enigma of dark matter wasn't enough, the universe holds another profound mystery, a force so bizarre and unexpected that it has challenged our very understanding of the cosmos: dark energy. For decades, scientists believed that the gravitational pull of matter would gradually slow down the universe's expansion, perhaps even leading to an eventual collapse, a cosmic big crunch. However, in the late 1990s, observations of distant supernovae revealed something astonishing. The universe's expansion is not slowing down, it is accelerating. The nature of dark energy is perhaps the most profound mystery in all of science. making up roughly 70% of the energy density of the universe and having profound implications for the fate of the cosmos. Our journey through the cosmos has taken us across vast distances of space and time, from the birth of stars to the grand structure of galaxies. But even as we explore the universe's farthest reaches, we encounter a fundamental limit to our cosmic vision, the cosmic horizon. Imagine standing on a ship at sea, the horizon marking the boundary between the visible ocean and the unknown expanse beyond. Similarly, in the vast ocean of the universe, there exists a cosmic horizon, a boundary beyond which we cannot see, no matter how powerful our telescopes. This cosmic horizon is not a physical barrier, but rather a consequence of the finite speed of light and the expansion of the universe. Because light takes time to travel, when we look at distant objects, we're seeing them as they were in the past. The farther away an object is, the further back in time we are looking. The cosmic horizon marks the point beyond which light from the early universe has not had enough time to reach us, even after traveling for billions of years. This means that there is a vast region of the universe, perhaps containing countless galaxies and cosmic wonders, that remains hidden from our view. The existence of the cosmic horizon reminds us of the vastness of the cosmos and the limits of our current understanding. It is a humbling reminder that there are still mysteries out there, waiting to be uncovered, realms beyond our current reach that beckon us to explore further. Our exploration of the universe has taken us from the smallest of particles to the largest cosmic structures. A fundamental disconnect remains between general relativity and quantum mechanics. General relativity describes gravity and massive objects, while quantum mechanics governs the very small. These two pillars of physics seem incompatible, like puzzle pieces that don't fit. This disconnect is most apparent in extreme environments, where a new theory is needed. The search for a unified theory is one of modern physics' greatest challenges. Such a theory could reshape our understanding of reality itself. As we conclude our journey through the cosmos, from the birth of atoms to the majestic sweep of galaxies, we are left with a sense of wonder and awe at the universe's vastness and complexity. We have uncovered many of the universe's secrets, yet countless mysteries remain, beckoning us to explore further. The cosmos is a tapestry woven with threads of light and darkness, of known and unknown. We have glimpsed the intricate workings of stars, the graceful dance of galaxies, and the cosmic symphony of creation and destruction. Yet we are still far from a complete understanding of the universe's grand design. The questions we have explored, from the nature of dark matter and dark energy to the search for a unified theory, are not just academic pursuits, but rather windows into the deepest mysteries of existence. They challenge us to push the boundaries of human knowledge, to explore the universe with curiosity and wonder, and to embrace the unknown. The cosmos is a vast and ever-changing landscape, full of endless possibilities. As we continue to explore its depths, we are certain to encounter new wonders, new mysteries, and new insights into the nature of the universe and our place within it. The journey of cosmic discovery is far from over. It has only just begun. Our journey through the cosmos has taken us from the fiery heart of the Big Bang to the swirling galaxies that grace the universe today. We've witnessed the birth of atoms in the crucible of the early universe, their transformation into heavier elements within the nuclear furnaces of stars, and their eventual incorporation into the planets, and indeed, the very fabric of our beings. As we reflect on this grand cosmic narrative, we are struck by a profound realization. We are all children of the stars. The atoms that make up our bodies, the air we breathe, the earth beneath our feet, were all once forged in the heart of a star, scattered across the cosmos in a supernova's dying breath, and eventually drawn together by gravity's patient hand to form our planet and all its inhabitants. This realization evokes a sense of awe and humility. We are not merely observers of the universe, we are active participants in its grand cosmic drama. Our very existence is a testament to the intricate workings of the cosmos, the elegant dance of matter and energy, and the extraordinary chain of events that led from the Big Bang to the emergence of life on this pale blue dot we call home. As we gaze upon a star-filled sky, we are reminded that we are connected to those distant points of light, not just by the laws of physics, but by a shared cosmic history. We are, in a very real sense, part of the universe, and the universe is a part of us. Our exploration of the universe has revealed a profound truth. The cosmos is not a collection of isolated objects, but rather an intricate web of interconnected systems, each influencing and influenced by the others in a delicate cosmic ballet. From the smallest atoms to the largest galaxies, the universe operates on principles of interdependence and interconnectedness. The dance of atoms within a star's core determines its luminosity, its lifespan, and its ultimate fate. The death of stars, in turn, enriches the interstellar medium with heavy elements, providing the raw materials for the next generation of stars and planets. Galaxies, those vast islands of stars, are not static entities but rather dynamic systems shaped by the gravitational interactions of their constituent stars, gas, and dark matter. Galactic collisions, though seemingly destructive, can trigger bursts of star formation, reshaping galaxies and giving rise to new generations of stars and planets. Even the expansion of the universe itself, a phenomenon that governs the large-scale structure of the cosmos, is influenced by the delicate interplay of gravity and dark energy, a mysterious force that permeates all of space, driving galaxies apart at an ever-increasing rate. Throughout our journey, we've encountered countless examples of this cosmic dance of interdependence, a reminder that every part of the universe, no matter how small or seemingly insignificant, plays a vital role in the grand cosmic scheme. For all the knowledge we've gained about the universe, countless mysteries remain, questions that continue to challenge our understanding and ignite our imaginations. The cosmos is a vast and enigmatic realm, full of wonder and surprise, and for every answer we uncover, new and even more profound questions emerge. The nature of dark matter and dark energy, those elusive entities that dominate the universe yet remain shrouded in mystery, is a profound challenge to our current understanding of physics. The search for a unified theory, a theory of everything that can reconcile the seemingly incompatible realms of general relativity and quantum mechanics, is a quest that has captivated physicists for generations. And then there are the questions that lie at the very edge of our current knowledge, questions about the origin of the universe, the nature of time and space, and the possibility of other universes beyond our own. These are questions that push the boundaries of human inquiry, forcing us to confront the limits of our current understanding and to imagine new and radical possibilities. The enduring mysteries of the universe are not a source of frustration, but rather an invitation to explore further, to delve deeper into the cosmos with curiosity and wonder. They remind us that the pursuit of knowledge is an ongoing journey, a never-ending quest to unravel the universe's secrets and to expand our understanding of our place within it. As we conclude our exploration of the universe, we are left with a profound sense of perspective, a cosmic awareness that transcends the boundaries of our everyday lives and connects us to something far grander than ourselves. The universe, in its vastness and complexity, can be a humbling and awe-inspiring place. It reminds us of the fragility of our own existence, the fleeting nature of time, and the preciousness of life on our planet. Yet, it also fills us with a sense of wonder and possibility, a realization that we are part of something truly extraordinary. From a cosmic perspective, our everyday worries and concerns seem small and insignificant. Wars, famines, and political strife fade into insignificance against the backdrop of a universe billions of years old and billions of light years across. This is not to say that these problems are not important, but rather to put them into a larger context, to remind ourselves that there is more to life than our immediate concerns. The universe invites us to embrace a sense of perspective, to see ourselves as part of a larger cosmic story, and to find meaning and purpose in something greater than ourselves. It is a story that began billions of years ago with the Big Bang, and continues to unfold today, a story that we are all a part of, whether we realize it or not. As we look up at the night sky, let us remember the lessons we have learned from our journey through the cosmos. The interconnectedness of all things, the enduring power of curiosity, the importance of perspective, and the endless capacity of the universe to inspire wonder and awe.